Let me demonstrate my screen. Mhm. Okay. Let's see if I find it. Okay. Okay. Last time we discussed the definition of stochastic semigroup. So let me recall it. And today we will consider examples of stochastic semigroups of operators, their structure. As usual in our lectures, H is a real separable Hilbert space we are considering a family JST. 0 is less or equal than S less or equal than T of strong random operators in H such that J S is equal to identity operator for all S greater or equal than 0. Second, J T1, T2 is identically distributed with J T1 plus S, T2 plus S for 0 less or equal than T2, S greater or equal than 0. Third, J T1, T2, J T n minus 1, T n are independent for T1 greater or equal than 0 less or equal than Tn for J T1 T3 is equal to J T2 T3 composition JT1 T2. We discussed the T2. We discussed that this composition in most cases is well defined, and in any time you have to discuss the possibility or existence of such composition. And 5 that J 0T H tends one can say in probability or in the gain on the situation. We call such a family by stochastic semigroup. JST is a stochastic semigroup. Last time we discussed a trivial example. When H is equal to a real line and JST H is equal H multiplying the exponent. Here is AT plus, oh, excuse me, minus B square over 2T plus BWT. WT, okay, let it be, and not S, but 0T. 0T. And we have a JST, then we substitute T by difference T minus S. But not always stochastic semigroup have such good structure. But still, we have a hope that, as in this case, we have an equation G 0T is equal to A G 0T dt plus B J 0T dWt. Then we have a hope that maybe a more general stochastic semigroup also can be represented in such a way. To understand this, let us consider the example of stochastic semigroup of unitary operators in Hilbert space. Suppose now that our H is equal to L2R. And as before, suppose WT T is greater or equal than 0 is a Wiener process. Let us define JST for all H as follows. For all H which belong to L2R, put JST from H at the point U is equal to H of U plus W T minus WS. So it is a shift of our function on the random number, on the increment of Wiener process. Since Lebesgue measure is shift invariant, then it is clear that JST is a random unitary operator. So now norm JST H is equal to norm of H. Shift is random, but still we have this one. Then one can ask what about the equation for JSTH? To understand what kind of equation we can expect, let us take H of the special form. I will take H smooth. So H from the test functions, it is infinitely differentiable and has finite support. Then one can try to consider a stochastic differential of H from U plus WT. And you can recognize here Ito formula. So using Ito formula now, I can conclude that it is equal to 1/2 of H2 prime U plus WT dt plus H prime U plus WT dWt. So in this case, we have such an expression, and what is remaining here? It is remaining to understand that now, due to the smoothness of H, one can say that H prime from U plus WT can be considered as d over du from J S T, excuse me, not S, J 0T H of U plus WT. That H2 prime U plus WT is equal d square over du square of J 0T H U plus WT. So now, if we consider in consider in N2R the differential operators. Differential operators denoted by A equal 1/2 of d square over du square, and B is equal d over du. Then finally one can obtain the equation for our semigroup. dj0t is equal a j0t. Oh, excuse me. dt plus b J0T dWt. And now one can think that this is the analog of the equation for stochastic exponent from example 1. Only one but essential difference is that A and B are now unbounded operators in the space L2R. And from this point of view, we need to be careful with this equation and just give every time the strong definition of what we are considering. So when considering such equation, we have to apply our stochastic semi-group GOT to some good function H. You remember we take H from this set of smooth functions, and then the result GOT from H is also smooth function. Then we apply these differential operators and have such equality. But formally, we still have a representation of our stochastic semigroup as a solution to a linear stochastic differential equation in Hilbert space with unbounded operators. It looks like from the first point of view now that how to proceed as follows. Take arbitrary differential operators here, and then consider the equation with so-called partial stochastic differential equation. And then try to find its solution and get the semigroup. But it occurs that we have to be careful in this way, and we can go this way, but not for every pairs of operators A and B. And let me explain the reason. So the next step is the stochastic partial differential equation. Equations. I will explain these things now on the simple example when we will consider such operators. Suppose that we have A multiply operator A is equal to A multiply even better to okay A multiply on d square over du square, and b is equal to y on d over du. Yeah. A and B are numbers, just numbers. Yeah. What we can expect, what we can expect already. Maybe we need to have a coefficient A greater than 0. You remember that in opposite case, even in the absence of the term of the first order, this one, the analog of the heat equation, d over d du, d, excuse me, du is equal a d d square du small square u has a solution, has a good solution in case when a is greater than 0. Yeah, this is important thing. So let us think that we have this case now and consider our equation. We want to have a solution. We want to have a solution of the equation like dj h a d2 d square j o t h dt plus b d du j o t h and then dw. And now let us think about this equation as about composition in some sense of two uh, two equations. One is related to the first term and second is related to the second. We already have a representation. We already have a representation uh, which arises here when we consider just shift of a function h on the increment of the Wiener process. In this case, one can see that here we get the following coefficient. Let me write here formally 1, and here we also have 1. But these coefficients are connected now. And let me say that now A is equal exactly uh, equal to b square over 2. Yeah. So from this reason, one can expect that in general, we must have some relationship between A and B in order to solution exist. But we can check this using the same method as was applied to heat equation in a deterministic case. Namely, let us use Fourier transform. So let us use Fourier transform. Denote Fourier transform J O T H. Let me. I will, as usual, denote by Fourier transform as a hat from lambda is equal to, for example, some lambda. Then for function v of lambda, we have the following Cauchy problem. D v lambda will be equal to, we have here a multiply on the derivative Fourier transform of the second derivative. You remember from the course of analysis that it is equal to imaginary unit I multiply on lambda square and multiply our v. Fourier transform of derivative is just a multiplication, yeah. It depends on dt. Remains. We don't show the dependence on t here, but maybe it is good to put this here, yeah. And then plus here we have b e lambda again just one time vt and then dwt. And then at least the first command can be slightly rewritten, and let me do this. So what we get, we will get here minus a lambda square v lambda dt plus b e lambda wt dwt, and the initial v0 of lambda, initial condition is h hat of lambda. This is again the equation for stochastic exponent, so one can think that we can easily solve it, and it is true, we can work with it. As before we did using E2 formula, despite that we have here complex numbers, everything is working, and one can write the solution to this Cauchy problem as a stochastic exponent. So we have the following relation. Wt lambda is equal h hat from lambda multiply on the exponent, and what we must have here. Firstly, the deterministic term minus h lambda square t, then minus, but we have here b multiply on, this is the this is the number which we have to put into square. So we will have here plus square lambda square b square lambda square over 2 t, yes, and then plus and here we have just e lambda I lambda b wt. That's all. Yeah. Now we have to we have to get from here the solution. To understand how to do this, let us pay attention to this term. Let us pay attention to this term. We have different cases. We have different cases. The first one case is the following. Suppose that this b square over 2 minus a is less than 0. In this case, let us denote this difference like is equal C, which is greater than 0. Then the representation of our solution, Fourier transform of our solution is following: is h prime lambda exp here is minus even. Let me. I just want you to recognize some already known things. So sorry, let us use much more appropriate expression. Let it be C over 2. Yeah. Okay. Then it is equal minus C multiply on T multiply on lambda square over 2. Yeah. Plus E lambda B W T. And I hope that now this exponent is written in such a way that everybody recognize here. Everybody must recognize here the let me Fourier transform of Gaussian density. Of Gaussian density P, what will be the variance? Here is the variance. You remember I specially wrote it in this way. CT, so CT, but also we have a mean, and what will be mean? This one. Put here minus only not with lambda, let us with lambda. Minus b multiply on wt. Yeah. Oh, so what happened now? We have a representation to our Cauchy problem. We have a representation. Let me. To our Cauchy problem as follows: Wt lambda is equal h lambda multiply on the Fourier transform of the following function. What does it mean? It means that our solution OT H of U is equal to convolution of these two things. Yes, so it is equal to convolution of H with this function. So one can say that it is equal to convolution with the Gaussian density with variance C multiplying T at the point U minus B WT. That's all. So you see, uh, since in this case our equation has two parts, one is related to heat equation and another one is related to shift, then one can say one can see that here we have in the final solution we have a presence of two things. Firstly, a convolution with heat semigroup with this P, and secondly, shift. By the way, this is a general principle, and you must meet it already, and you will meet it in your mathematical studies. That sometime, if you have a differential equation which contains different parts in the right-hand side, then the solution can be obtained as a composition of solutions to these parts separately. Yeah? In some sense, composition, of course, you must be careful. But at least now we have a solution. Yeah, this is a solution to our initial problem, and here is a representation of our semigroup. It is and really it contains some integral operator, this convolution. So it is already a rather complicated thing. Now you remember we considered just one case. Now the second case, but it will be very easy for us. Now consider a case when b square over 2 minus a is equal to 0. But we already recognize this case because you remember it is exactly the relationship which arrives in the shift formula. So now I can write answer h of u is equal h of u minus BWT. You see, here everything is trivial. We already have such a representation, and it is consistent with the previous case, because in this case c equal to 0, so we have p0 is equal to delta function at point 0, and then we have no special convolution with heat kernel. We just have a shift. That's all. So in this case, we also can write the solution to our Cauchy problem, and it again occurs to be a stochastic semigroup. Yeah. And the last case we have to investigate is the following: e square over 2 is greater than a, so it is greater than 0. One can do the same up to this step. So for Vt of lambda, you have a representation. Vt of lambda is the h hat lambda multiply on the exponent. But what we have here? We will have here something wrong. Why? Let me say put here C1 lambda square T O2 and minus E lambda BWT. This term is nothing of interest now, but this one is because now C1 is greater than zero, and maybe you have to understand that this is not a Fourier transform now of the good kernel. Yeah, because of this, to have to have VT of lambda to be a good Fourier transform, we need some additional properties of h hat of lambda. For example, of course, if h hat decreases at infinity faster, then this one is an exponent in this power, then one can get a solution. And those of you who studied partial differential equation maybe understand what happened. We need now we are working with the heat equation in the backward time. So we have like roughly speaking, non-mathematically, backward convolution. So if h hat already is modified by convolution with Gaussian kernels, then we can go back and find solution WT. But in general, no. So you see that in this case we have no solution in general. Is no solution. So one can see that when we are looking for stochastic differential equation for semigroup, one can expect that such equation can be a stochastic partial differential equation, for example, and that this solution to this Tokoshi problem from this equation will give us our random operators. But we already investigated with you that not every stochastic partial differential equation is related to the good solution for Cauchy problem, and cannot construct stochastic semigroup from the arbitrary stochastic differential equation. One can check a very good book on this thing. Maybe one of the most known book is Etienne Pardue and Jerzy Zabczyk. On partial stochastic differential equation in Hilbert space. And you can see that if you consider general case, so if you want to define the stochastic semigroup using this approach, so if you want to consider the general case of stochastic partial differential equations of the second order, linear one, plus here L and here let me B J O T H D W T, then it must be the following, that L minus 1/2 b star b must be less than 0. Yeah? Okay. Okay. So we have such kind of stochastic differential equation. Then it will give us the stochastic semigroup as a solution to Cauchy problem. Here you see this inequality. This is operator inequality. This is L is an operator of the second order. B star multiplied B is an operator of the second order. So we must have this inequality for the operators. Of course, it can be relaxed. There are some sectorial operators and a large theory which you can find in those books which I mentioned. But this example give you a feeling that not always stochastic partial differential equation give us an example of the stochastic semigroup. Now let us begin to think in the backward direction. One can ask, okay, since the stochastic partial differential equation is a source for stochastic semigroup, or stochastic differential equation is a source of stochastic semigroup, then maybe when we have a stochastic semigroup, one can try to recover the corresponding equation. And it occurs to be true again in not all cases, but in a lot of cases. So let us go to the recovering equation for stochastic semigroup. Again, let us start from the example. So let us consider a very simple example which we discussed. This is a stochastic exponent. So again, H is equal to R. Again, we have, suppose that we have two numbers A and B, and now we have the following semigroup JST as is a multiplication of H on the exponent. Here we have AT minus B squared over 2 T plus B. Again, I did the same mistake. Let me now write it in the right way. Here is A T minus S plus B squared over 2 T minus S, excuse me, minus and plus B minus WS. Since this is a simplest example of stochastic semigroup for us, we have just to understand how to recover from this expression, how to find A, B, and W. Yes, because we need the equation with increments of W. First of all, to understand this, let us consider even simplest case, deterministic case. So, if I have e in power a t minus s, how one can reconstruct a from here? This is a simple analysis. Everybody know that maybe a can be found here as follows. A is equal to a limit under t tends to 0 plus EAT minus 1 over t. Yes. And we already discussed this just noting that for deterministic semigroup we have a notion of generator. And even in general case, for good deterministic semigroup, one can find its generator using the same limit. Okay, it's good. But what term? What to do with this term? Firstly, what we have no theorem in analysis which give us the limit containing Wiener process. This is the first one. Second one problem is that to recover Wiener process, we have to recover all its increments, not only at zero. So the procedure must be very different from this one. This is too easy to be generalized on the stochastic case. We have to find something new. And it can be done. It can be done. For example, suppose that I want to have not A, but AT. How I can proceed? Let us fix T for a moment. Okay. Let us fix T greater than 0 and consider partition. Take a partition. Take a partition. 0 equal to 0, t0 less than t1, and as usual, less than tn, which is equal to t. Then let us analyze the following things. Sum from k equals 0 to n minus 1. Here e a tk plus 1 minus tk minus 1. Okay? I am organizing such sum. Now, let it be exercise for you. Please prove that it tends to AT when the maximum diameter of our partition, maximum tk plus 1 minus tk, tends to 0. Tends to 0. Please check this. It is not too hard using this unuseful limit for us. Yeah. Let us write this in terms of the semigroup. At least in this deterministic case, it means that if I take any h, now it is a number, And consider the sum from k equals 0 to n minus 1. And here we have j tk plus 1, tk plus 1 of h minus h. Then it will go to 80 maximum of tk plus 1 minus tk tends to 0. That's all. This is the idea. You see? Using this idea, we can go further. Why this idea can be fruitful, looks fruitful? Because you remember, we said that we want to recover increments of the Wiener process on all intervals of the time. And here we have the increments of our stochastic exponent on all interval of the time. Yes? So please do this exercise, and then you will understand that this idea can work. And we will apply it to more general stochastic semigroup at the next lecture tomorrow. For today, that's all. Thank you for your attention. Maybe somebody have questions or comments, please.